Okay, so we're very happy to have today Idan Mehalel, and he's going to talk about high-quality sets of questions in a 20-question game. And this is a direct track to PhD transfer seminar.
Thank you. Hi everyone. My name is Idan. My advisor is Yuval Filmus. This is my direct track to PhD transfer seminar. So today I'm going to present to you our work about the 20 questions game. What we mainly do is to answer some open questions suggested by the paper 20 Simple Questions from 2017, which is by Yuval Dagan, Yuval Filmus, which is my advisor, Ariel Gabizon, and Shai Moran. So I just want to go over the agenda for the talk. We'll have 5 parts. We start with the introduction, in which I will review the game itself and some previous results from the 20 Simple Questions paper, and also our contribution. Then I will give some more necessary details on previous results. And then I will try to give some motivation for our contribution. And then I will give some more interesting, I think, interesting enough details about our contribution. And we will finish with some open questions for future research. So we begin with the introduction. So what is the 20 questions game, the basic 20 questions game? So maybe some of us or most of us are already familiar with this game. It's this game, maybe you played it on the bus, on school trips, or in the car with your family. It's this game where one of the participants has to think about some object in the universe, and the rest of the participants have to guess what is the object, what is the secret object in as few questions, as few yes-no questions as possible. Namely, in less than 20 questions, in less than 20 yes-no questions. So more formally, the game is, in our context, played between Alice and Bob. So Alice picks a secret element X from some predetermined set of elements, which we call Xn, which is of size n. For example, it could be all possible food in the world. And Bob's goal is to reveal X within as few yes-no questions as possible. So how do we represent a question? So the question is X in some subset of the universe Q is simply represented by the subset Q. So let's say Bob wants to ask Alice if the secret element she think of is a fruit. So we can simply send Alice the subset of all fruits, and that will represent that question. So let's see an example of how the game can go. So let's say that our universe is food, and the secret element Alice pick is an apple. So Bob starts by asking a yes-no question. So he can, for example, ask, is X a fruit? So if Alice says no, then the game should somehow continue. But we know she's going to say yes because an apple is a fruit. So she will say yes, and then Bob asks another question. For example, he can ask, is X an apple? So if it's not an apple, so Alice says no, but we know that it is an apple. So in this case, the game is finished, and Bob has revealed X after 2 questions. So we can see that this game is represented by a binary decision tree. So each internal node represents a question, and the edges simply represents the answers, the possible answers, yes or no. And the game is finished when we arrive to a leaf, which represents a single object, which if we arrive to a leaf of the object X, so it means that X is the secret element that Alice picked. So this is an example for the game, for this basic game. But what actually we are interested in is a variation called the probabilistic 20 questions game. So in this game, what happens is that first Alex picks a probability distribution pi over the set of elements xn, and she reveals pi to Bob. And then Alice draws the secret element X from pi. So she doesn't just pick an element, she draws it directly from the distribution pi that Bob knows. And now Bob's goal is to construct a strategy that minimizes the expected number of questions required to reveal X. So if they will play a lot of games with the distribution pi, so the average number of questions will be minimized. That is Bob's goal. So how can he fulfill that goal? So actually, Huffman's code gives optimal strategies for all distribution. That is, if Bob is going to construct his strategy with the Huffman code, Huffman tree, so his success is guaranteed. He's going to construct an optimal strategy for sure. So this maybe seems solved. So if that is the case, what can we further ask about this? So let's try to answer that with another example. So in this example, let's assume that Alice picks, the distribution that Alice picks gives 0 probability to all elements which are not fruit. Okay, so the distribution pi that Alice picks is of this form. So if y is not a fruit, the probability it will get to be picked is 0. So in this case, our universe, in this specific case, our universe is actually being reduced from all possible foods only to all possible fruits. So this is a reminder for the form of our probability. Now, I wanted to, we will take another look on the first strategy from before. So this was our strategy when we talked about the basic 20 questions game. Now, if we know that our distribution is of this form, so the first question is X a fruit seems completely redundant, right? There is no point in asking it at all, not as a first question and not as any question, because we know that y has to be a fruit, because if it's not a fruit, its probability to be picked as a secret element is 0. So we can remove this question, and in this case, to improve the strategy by one question easily. And there's no point in asking this question at all, at any point of this game, because X has to be a fruit. So there's no point in asking if it is a fruit. So what is the conclusion? That given the distribution pi, a specific distribution, some of the possible questions are redundant. So we said that a question is represented by a subset Q of xn. So that means that there are in total 2 to the n possible questions. But if we are given a specific distribution pi, a lot of those possible questions may be completely redundant and should not be used in the strategy that we construct, in our optimal strategy. So that may lead us to think maybe there are questions which are completely redundant. That is, maybe they are redundant for all distributions. So maybe there are questions like, is X a fruit that any distribution Alice will throw on us, on the universe, we will not have to use them. We will always be able to construct an optimal strategy without using those redundant questions. And if so, so how many of those questions there are? So
just a quick question. So this is a very, if I may, will you talk also about a more robust notion that that approximates optimality, or you're focusing here on the?
No, so what you're talking about is actually, yeah, it is answered or being conducted in the original in the paper 20 simple questions, but not in this work. So in this work, we're talking about strategies that gives optimal results. Okay. Okay, so it's worth mentioning that a strategy generated by a Huffman code may use any arbitrary question, Q, which is a subset of Xn. So the problem here with the Huffman code that it may use any arbitrary questions. There are no redundant questions in Huffman code. So if Bob is going to construct his strategy using a Huffman code, he may use any arbitrary possible question of the 2 to the n possible question. So that is the problem with the Huffman code here. So in the paper 20 simple questions, Dagan et al. Asked this formally. So the question they ask is, one of the questions they ask, is there a set of high quality questions, Q, which is a subset of the family of all 2 to the n questions, which is significantly smaller than 2 to the n, and yet one can construct optimal strategies for all distributions using only questions from Q. So to deal with this question, it is easy to denote Q of n to be the minimal number of questions required to construct optimal strategies for all distributions over Xn. So we said that a Huffman code may use any arbitrary question, and the success is guaranteed to always be able to construct an optimal strategy for any distribution. But the question is whether this minimal number of questions required to always construct optimal strategy for any distribution we will get is maybe smaller. So any questions so far on this question or on anything?
Yeah, again, maybe it's a bit premature, but if you consider, say, efficiently sampleable distributions, would it change the answer, or in general, small sets of distributions?
Sorry, again?
Suppose that you consider efficiently sampleable distributions instead of all distributions. To what extent are the conclusions sensitive to such a restriction?
So you're asking if we going to take, instead of all distributions, only some types of distribution or a subset of all distribution is...
like ones that are efficiently sampleable.
Okay. Yeah, so we didn't study this problem in this research, so this work, so I don't know, but maybe.
And again, maybe you can motivate. I mean, it seems like it's a very natural question that must have some motivation, but can you spell it out if you're aware of any?
I'm not really aware of a formal one, but I think it's just interesting to understand if it's necessary to, let's say you have let's say in some condition, in some situation, you have to, let's say, bring a bag of all questions you might going to use when you, let's say you meet Alice at the playground, and she tells you, listen, you have to bring a bag with all the questions you might going to use, and you don't know what is the distribution I'm going to throw on you. So I think it is interesting to understand if we really have to bring a very big bag with all to the end questions, or maybe we can bring a smaller one. But I'm not aware of some practical motivation for that.
Okay.
Yeah, so
maybe I have a suggestion actually. Maybe if there is noise and you want to also encode the messages, so a small set you can correct more errors. You have only a small set of messages.
Right, but then you might as well consider interactive coding. So this thing comes up in distributed computing, where it represents asymmetric communication. So like Bob is only allowed to send bits because communication in this direction is very hard, but Alice is allowed to send whatever, but still we want to minimize the communication. So I think it's like a made up setup, but it does appear in the literature.
Okay, so you're saying that there is a simple to describe communication complexity problem which this solves?
Sort of, but if you think of it this way, then I mean, this is not really the correct problem to solve.
Okay.
Okay, thank you for the questions. So I will move on. So this is the, so far, let's say, the introduction of the introduction, just explaining what we're talking about. And now we'll give the previous results and also our contribution. So this is a reminder for what is Q of n, is the minimal size of a high quality set of questions. And as we said, in this context, high quality means questions that allows to construct optimal strategies, not some approximation to the optimal, but really optimal strategies for any distribution. So the question in really short is whether Q of n is much smaller than 2 to the n, than the size of the set of all possible yes/no questions. So in the paper 20 Simple Questions, Dagan et al. Showed that the answer to this question is positive by showing the following theorem, that it holds that Q of n is at least 1.232 to the n and at most 1.25 to the n, up to some sub-exponential factors, which we do not care about. We are interested in the base of the exponent of Q of n for different values of n. So they show that it is at most 1.25 to the n, so it's much smaller than 2 to the n, and it has to be at least 1.232 to the n. And moreover, they show that if n is of this specific form, which is 1.25 times some power of 2, then Q of n is exactly 1.25 to the n, again up to a sub-exponential factor. And we use this approximation notation to state equal up to a sub-exponential factor. So this is their result. And they raised the following open question. So as we say, they calculate Q of n for n of this form, for n of the form 1.25 times some power of 2, and for this form of n, they show that Q of n is exactly 1.25 to the n. But generally for n, they give an upper bound of this 1.25 to the n is the upper bound for Q of n for any n. So they ask whether we can actually calculate Q of n for any n, not just for n of this form. So this is the question they raise, and they also conjecture that there exists a function g from the real segment 1, 2 to the reals, such that if n is of the form beta, for beta times some power of 2, where beta is some number between 1 and 2, then Q of n is exactly 2 to the g of beta n. So this is their conjecture, and for example, this result already implies that g of 1.25 is exactly log of 1.25. So this is their conjecture, and our first main result is that their conjecture is correct. So we show the following theorem, that if n equals to beta times some power of 2, where beta is some number between 1 and 2, then Q of n is exactly up to a sub-exponential factor 2 to the g of beta n, where g of beta is this following function, which I will not elaborate on it now. Later, I maybe just give a bit intuition about what it represents. So it's also worth mentioning that a similar formula to that one was conjectured already by Dagan et al. In some of their unpublished notes. We made some modification for their formula and proved it. So this is our first main result. And we also have a corollary from this theorem, from this first main result, from this formula for Q of n, which improves the explicit lower bound on Q of n. So this is the corollary, that for any n, we have the following lower bound, that Q of n is more than 1.236 to the n, up to a sub-exponential factor. And just a reminder that the previous lower bound gave by Dagan et al. Was 1.232 to the n. So it may seem a bit weird because our first main result give a formula for Q of n, which states what is the value of Q of n for any n. So why do we need a lower bound if we have a formula? So the problem with the formula is that we do not know, we have the formula, but we do not know how to numerically calculate it. But we can give a numerically a better lower bound using the formula that we have shown. So this is this is our first main result. And we also have a second main result, which I will only state. Any questions about results so far? Okay, so we also have a second main result, which again, I will just state and I will not elaborate it further. So we generalize results from DFGM 17, which is the 20 simple questions paper on QFN to the setting of multiple choice questions. So in this setting, we don't have only yes and no questions. We have questions that has D possible answers. Like a multiple choice exam in university or school, we just have, instead of yes or no as answers, we have 1 to D possible answers, and we call this the DRE setting. So in the DRE setting, the questions asked by Bob have some number D possible answers. So if we talk about, for example, the binary decision tree that we have seen in the beginning of the talk, that this is the way to represent a game. So in the DRE setting, instead of a binary tree, we will simply have a DRE tree. So every node will represent a question, and instead of only yes and no as edges, we will have edges 1 to D. Each states a possible answer to the question. So we denote with the QD of n the equivalent value of Q of n in the DRE setting. So QD of n is the minimal size of a set of questions, which always allows to construct optimal strategies for any distribution in the DRE setting, in the setting that each question has D possible answers instead of only 2. So we show the following theorem that for any n and for any D which is asymptotically smaller than n over log square n, we have that QD of n is at most this expression to the n, which is less than 2 to the n, up to a sub-exponential factor. And moreover, if D is fixed, then for infinitely many n values, the above inequality, this inequality, actually holds as equality up to sub-exponential factors. So if D is fixed for any D, we have infinitely many n values that for them, we know the exact value of QD of n. And generally, for any n, we know that always the value of QD of n is less than 2 to the n. So this lower bound of less than 2 to the n it vastly improves on the trivial upper bound, which is d to the n over d factorial, which is, this is simply the number of all possible questions with d answers. So this is our second main result, and by that we finish the introduction and can go to part 2. So any questions so far?
So you'll probably get to it soon, but I'm just curious if the set of queries that you show and also in the previous works, is it kind of constructive or is it just a random set works?
Yeah, so you ask if, let's say we know that we have 1.25 to the n questions which allow us to always construct optimal strategies. So you ask if we know what are those.
You can point them out, yeah.
Yeah, so actually no, and this is, I think, a very interesting open question to find those questions. No, the proof is probabilistic, so no.
Okay.
Yes, so I asked Nagalon in 2017, and he thinks it would be quite difficult.
That what? He thinks what?
The de-randomizing the construction would be quite difficult.
But does it? Are there any similar, qualitatively similar results for other questions in other domains? I mean, it sounds very fundamental but specialized. So is there any other domain in which the same kind of questions were asked and answered in a qualitatively similar way? Like finding some universal set of functions for some purpose, or my question is whether it's related to something else.
So I'm sure you can find a paper of Erdős.
Okay. My question is, what is the paper of Erdős about? Another question, so can you get not this bound, but something non-trivial upper bound for the multiple choice case in a black box way using the binary case? Like anything better than the naive thing? Or you will not get,
So maybe the first thing to notice that even in the binary case, we do have an explicit set of questions of size square root 2 to the n. And probably you can do something similar here.
Yeah, that's.
But if, say, I have 4 options and now I try to do it, so it's like, and now I try to reduce it to the binary case, will I get something non-trivial or not? I don't have good enough intuition. Okay, never mind. Yeah, because there is this.
You find an explicit set of questions, you mean? Or
okay.
No, not an explicit. Just.
Like if you have a good set of questions for d equals 2, can you use it to generate something for a larger d? That's an interesting question. We haven't considered it.
Okay.
Okay. Thank you.
Now we got us curious, so we now we'll stay until the end to see how it's done.
Great, thank you. Okay, so now just before we continue to part 2 of the talk, so I just want to say that the next 2 parts are just a bit technical, so I want to go over about what we're going to talk in those parts. So what I want to talk about is that, again, so the Gantel showed that Q of n is at most 1.25 to the n for any n. So this is a main interesting result that shows, again, that we don't need all 2 to the n questions in order to always construct optimal strategies. And they also show that for n of this specific form, Q of n is at least 1.25 to the n. So actually what remains open is what is the exact value of Q of n for other n values. So the natural thing to try first is to take their proof and try to adapt it for other values of n, and maybe we can show this lower bound also for other values of n and not just for that form of n. So we're going to try and do that, and by that give some motivation for our result, which gives a formula for Q of n. So because if that was possible, so there would be not a lot, there wouldn't be a point in our result if we could simply adapt their proof to find this lower bound for other n values. So in order to do that, what we are going to do in part 2, we review their proof for the lower bound. And then in part 3, we will try to apply similar proof for n of other forms. And hopefully we will understand why it doesn't work, and we have to take some other approach in order to understand what is Q of n for other values of n. So as I said, if when we try to apply similar proof for other values of n, we will fail. And the conclusion is that we should calculate Q of n in some different way. So let's go over to move on to part 2. So we give some more details on previous results and mainly review this lower bound of 1.25 to the n for specific n values.
Maybe, sorry for interrupting again, but just, you recall this classical result of Hoffman that shows that, so will you say a few words about it, just to remind us what's the idea?
So you mean what is the class?
Showing that every distribution, so Hoffman's result shows how to construct an optimal strategy for every distribution, right? So can you say a few words about it, just to explain the idea? I think we taught it, some of us taught it, but including myself, but I don't remember it. So.
Sorry, what? You said something?
This is an algorithmic question.
But Hoffman, again, just the inadequacy of Hoffman for this purpose, right? So you said that Hoffman uses Hoffman's strategy does not solve the problem. So I want to recall what is Hoffman. So it could have been the case that Hoffman already has the features that you want, right? So I just want to briefly recall how Hoffman works and why it does not give us what we want. It's not important if it's not, if it takes too much time, forget about it.
No, yes. So the idea is that the way Huffman codes work just may use what Huffman codes does. It picks, if I remember correctly, the lowest probability elements, and then put two edges between, and then treat them as one element in the next iteration. And this process may construct any possible question from the 2 to the n questions. So we want to try and understand if it is possible to construct always optimal strategies without a process that may use any arbitrary question. So but the question is
Hoffman, what I'm confused about is that isn't Hoffman in some sense unique, or maybe you relax the setting of Hoffman coding by considering more general queries? That's maybe my point of confusion.
So Hoffman conversions are not unique, and they're even not. Hoffman algorithm is non-deterministic. It could produce many different trees, but it's known not to produce all the optimal decision trees. So they have extra properties. The problem with Hoffman's algorithm, for what we do, is that it is bottom up, whereas we really need a top-down approach to reduce the number of questions, because it's hard to control the questions. But you can easily show that the Hoffman's algorithm can basically get any kind of question at the root.
Okay, thanks.
Okay, thank you. Yes, so now we will review some more details on previous results and the lower bound for some n values. So in order to do that, we need to talk about a reduction made in the 20 simple questions paper. So the bounds on Q of n, also our new lower bound and Dagan et al.'s bound, are obtained by reduction from the problem of calculating Q of n. So the reduction is from calculating Q of n to calculating a value called the minimal maximum relative density of n, which we'll now shortly define. So in order to define it, we need to define two more simple concepts. So the first one is a type of distributions, which called dyadic distributions. So a distribution mu is a dyadic if for any element x in xn, the probability of x is 1 over some power of 2. So if that is the case, our distribution mu is dyadic. And we say that a subset of xn, q, splits mu if mu of q is exactly f. So if the total probabilities of all the elements in q is exactly half, we say that q splits mu. And now we can define the maximum.
Yeah. You also don't, so you don't allow a probability 0 element?
Yes, I all non-zero elements. Yeah, you're right.
All are non-zero. Okay.
All non-zero elements. Yeah. Okay. Thank you. So the maximum relative density, which we call in short MRD of mu, is defined as follows. So it is denoted by a rho of mu, and this value is defined as the number of size I split in sets over all subsets of size I. So the number of size I split in sets, when splitting sets again is all sets that for them mu of the total number of the total probabilities of the elements in this set is exactly f over all subset of size I, when I is chosen to be the I that maximizes this expression over all i's from 1 to the n minus 1. So this definition is defined on a dyadic distribution. Okay, so this distribution mu is dyadic. And if we talk about any expression of this form, number of size I splitting sets over all subsets of size I, we simply call it a relative density, not maximum relative density, because it is not necessarily the maximum one. So this is just a reminder for what is the MRD. So we denote with a rho minimum of n, the minimal MRD across all the dyadic distributions over n. And the reduction to minimal MRD states that Q of n is actually exactly up to a sub-exponential factor 1 over the minimal MRD of n. So this is the reduction, and they use it to upper bound and lower bound Q of n, namely to lower bound and upper bound the minimal MRD of n, because this is 1 over the minimal MRD of n. And we will now shortly discuss the lower bound of Q of n for n of this form. So we will talk about lower bounding Q of n when n is of the form 5 times some power of 2. This is exactly like 1.25 times some power of 2. It's just easier to consider it in this form. So again, just a reminder for what is the MRD, a number of size I splitting sets over all subsets of size I when the I is taken to maximize this. And the minimal MRD, the rho minimum of n is defined to be the minimal MRD across all the dyadic distributions. And the reduction states that Q of n is exactly 1 over the minimal MRD of n. So by this reduction, if we want to lower bound Q of n, it is enough to upper bound the minimal MRD of n. So how Dagan et al. Did this, they constructed the distribution mu, and then found the minimal MRD, the MRD of mu, the maximum relative density of mu. So the MRD of mu is at least as the minimal MRD. So this will give us an upper bound on the minimal MRD of n. So let's just take a look on this distribution they constructed that gave this bound. So it is convenient to look at the dyadic distribution in a form of a binary tree, because we can simply represent an element that has a distribution 1 over 2 to the L as a leaf at depth L. So this is our form of n, and what they did is they constructed a complete binary tree that has 2 over 5n, which are exactly 2 to the k leaves, which represent 2 to the k elements with probability 1 over 2 to the k. So we call those large elements. But we want to have a total of n elements. So what they did is the last leaf, they just split it into a tail of 3 over 5n low probability elements like that. So this is our distribution mu. So if we look at it, we can see that any splitting set which does not contain the tail is exactly of size 1 over 5n, right? Because we have 2 over 5n large elements, high probability elements. And if we want a splitting set, we have to take exactly half of the elements because they all have the same probability. So this distribution, when we want to calculate its MRD, this is what we want to do, we get the following, that up to complementation, each splitting set is composed of 1 over 5n large elements. So all the splitting sets which does not contain the tail. And because we don't care about sub-exponential factors, we can actually ignore the splitting sets which contain the tail, because this is up to complementation. And then what we get is, as we say, the minimal MRD of n is at most the MRD of mu, and the MRD of mu is from the large elements, we take exactly half, which is 1/5n. And this is the only possible size of a splitting set, which takes exactly half of the large elements. So we take 1/5n large elements, and we divide it by all subsets of size 1/5n. So this is roughly this expression, which is 4/5 to the n. And then by the reduction, if we take that 4/5 to the -1, so we get a lower bound on Q of n of 1.25 to the n, which applies for n of this specific form. So this is the lower bound for n of this form of 1.25 to the n, which matches the general upper bound of 1.25 to the n. But again, it only for n of this form. So what we're going to try to do is to imitate this distribution and show a similar lower bound also for other forms of n. So any questions on that? Okay, good. So in part 3, as I said, we will try to adapt this proof for other values of n. So as we said, the Ryan et al. Showed this upper bound, and we want to check if we can prove a lower bound of 1.25 to the n also for n not of this form. So for example, we take n, which is 7 times some power of 2. It's if we want to conform with beta being between 1 and 2, so it's the same as 1.75. Again, it is just easier to consider it in this form. So what we want to do, we want to imitate the distribution mu from earlier, which had 2/5 large elements, and we took half of them to construct a splitting set. So what we want to do is to give the same probability to any large element. So we want to give a probability of 1/2/5n to any of the large elements. But in this case, because of the form of n, we get that this probability is not dyadic. It's 1/7/5 times 2 to the k. And this is not a probability of the form 1/some power of 2. So we can't do that, because if we will do that, we get a distribution which is not dyadic. But we can try to fix it. How we can try to fix it? We can just add another different high probability. Instead of all elements, all high probability elements having probability of 1/2 to the k, we add another, just only one different probability, and this will be fixed. So maybe we can hope that because we only added one different high probability, maybe we can still use this distribution to derive the lower bound of 1.25 to the n. So we will use two different high probabilities. We will have large elements exactly as before with 1/2 to the k probability, and we also add mediocre elements, which will have 1/2 to the k plus 1 probability. So let's take a look at it as a binary tree form as before. So we construct a binary tree with 2/7n, which is exactly 2 to the k leaves, which are the large elements. So as we said, we want, in order to get 2/5n large elements, we want to add mediocre elements. So we split that set of large elements into two sets, one of size 6/35n and one of size 4/35n. And what we do is we split those large elements, each one of them, into two mediocre elements. And so we get 8/35n mediocre elements, and the rest is a low probability elements tail. So this imitates the distribution mu from before. We have 2/5n large high probability elements, and the rest is a low probability tail. But here we have two different high probabilities. Yeah, so this is, we call this distribution nu, and this is nu in a binary tree form. So now let's see if we get the same lower bound. So we can do the same as before. We consider splitting sets that takes exactly half of the high probability elements. So in this case, it will be half of the large elements and half of the mediocre elements, which really sums up to 1/5n elements. So the relative density in this case will be taking from the large elements half and from the mediocre elements half, dividing it by all subsets of size 1/5n, and we get roughly this expression, which is indeed 4/5 to the n, which is exactly as we got before. So if this really was the MRD of the distribution U we constructed, then it would be applied that Q for n of this form is really at least 1.25 to the n. But unfortunately, it is not, because just a reminder for the definition of MRD, it was the number of size I splitting sets over all subsets of size I, but this I is taken such that this expression is maximized. So previously, there was only one type of splitting sets, those who take exactly half of the large elements. But here, because we have two types, this messes things up, and we have a lot of different sizes of splitting sets. So this is essentially the reason why the proof doesn't work for other n values, and this is what gives the motivation, I think, for our result. So we even can give a simple example for why this is not the MRD. We can find a splitting set size that give a higher relative density, and thus this could not be the MRD. So we can consider splitting sets with 4/35n large elements and 2/35n mediocre elements, which sums to a total of 6/35n elements. So you just trust me that those are really splitting sets. So again, we take 2/3 of the large elements and only 1/4 of the mediocre elements, and divide it by all subsets of size 6/35n. We get roughly this expression, which is strictly higher than 4/5 to the n. So 4/5 to the n cannot be the MRD of this distribution. And so this technique of proof doesn't work if you're dealing with other values of n. So actually, we can say that what they did in the 20 simple questions paper is they show the upper bound of 1.25 to the n, and they found the specific n form of 1.25 times some power of 2, that in those n magically things get along, and we get a lower bound that is somehow exactly as the general upper bound. But when we talk about general n, this approach doesn't work, so we need to find some other way to understand the value of Q of n. So this is the motivation, and now if I have time, I just want to give, I have a few minutes, or I just want to give a few more details about our results, which I think are interesting enough, and then we'll finish the talk. So just any questions on that before I move on? Okay, so I just want to give a few more details on our contribution. So we give actually a formula for Q of n. As we've said, by the reduction in DFGM 17, it is enough to actually give a formula to the minimal MRD of n. So calculating it is a combinatorial optimization problem. We have to find the dyadic distribution mu that brings this value to the minimum. And our work shows that for any n, which is beta times some power of 2, the minimal MRD is this value, 2 to the minus g of beta n. So this is our result. So we can basically say that what it does, it reduces the problem of calculating the minimal MRD of n to this optimization problem over sequences in the real segment 0, 1. So what we are working on here are sequences. Here we have C, and here we have alpha, which are sequences, infinite sequences on the over the segment, over the real segment 0, 1. And moreover, so because that the minimal MRD of n is 2 to the minus g of beta n, calculating the value of the minimal MRD of n of this form is reduced to calculating g of beta. So if we calculate g of beta, we actually know the minimal MRD of n for infinitely many n values, namely for all n values of this form. So, okay, I will skip on that. And so I just want to say, to finish the talk, I said that actually we have a formula for g of beta, but we don't know how to calculate it numerically. But what we can do is we can find explicit lower bounds on it. So if we lower bound minus g of beta, because q of n is 2 to the g of beta n, if we lower bound minus g of beta, we get an upper bound on q of n and vice versa. So how can we lower bound minus g of beta? We can find a sequence alpha, which is feasible for any sequence C. So trust me that the sequence alpha, which gives alpha I equals half to any I, is always feasible. And therefore, minus g of beta is always at least this expression, which is at least minus log 1.25. So by this simple lower bound on minus g of beta, we can derive the upper bound of q of n, which is at most 1.25 to the n, which is a main result in DFGM 17. And if we want to lower bound minus g of beta, if we want to lower bound q of n by upper bounding minus g of beta, we can actually get an explicit, a better explicit lower bound than what was given by Dagan et al. So how can we upper bound minus g of beta? We can define a finite sequence C and find the sequence alpha that maximize it. And how can we do that? We can just use Lagrange multipliers. So in our work, we simply find a specific sequence C that gives a value of, that gives the upper bound on minus g of beta, which implies a new lower bound of q of n more than 1.236 to the n. So this is about bounds on g of beta, which implies bounds on q of n. And this is pretty much it. So I just want to finish with some open questions for future research. So a main open question, of course, is if we can numerically calculate g of beta. If we can do that, we can know the exact up to sub-exponential factor numerical value for q of n for any n of any form. And we don't know even more basic stuff. For example, we don't know whether G is continuous. Our work shows it is upper semi-continuous, but we do not know if it is also lower semi-continuous. And it holds that the bound of 1.25 to the n, the upper bound of 1.25 to the n is tight for a general n. But our new lower bound of 1.236 to the n, we don't know if it is tight for a general n, so it maybe can be improved even for a general n. Maybe it could be raised. And we also can ask whether we can generalize the function g to the DI setting. And that's pretty much it. So thank you very much for listening. And if you have any questions, I'll be happy to discuss.
Okay. Thank you, speaker. So before questions, I just want to say, you asked the questions previously. Is this related to any other problems? So there's a problem of finding the best fiber. So fiber is the hitting set for maximal empty chains. And this 1.25 to the n lower bound actually comes from there. I mean, I think we found it independently, but it also comes from there. So that's some kind of connection. Okay. Yeah, questions?
So how can you explain directly a connection to anti-chains? Is it obvious that this question is connected to anti-chain, maximal anti-chain?
So if you have a distribution with no zero elements, so one often asked whether we should allow elements to have a probability 0. So the answer is no, because we can reduce to the case of no zero probability elements. So now suppose that you have a dialectic distribution with where no element has probability 0, and you look at all the splitting sets. So all sets of probability exactly 1/2. Okay, so this is the maximal anti-chain.
Okay. Cool. And in other contexts of distribution-dependent algorithms, say learning in general, and now if you want a universal set of algorithms that applies to every distribution, right? You can think any kind of learning problem is distribution-dependent, or many other problems. The question, so this is like a decision tree. It's a very generic algorithmic object. My question is whether the same maybe as an application of this to learning, for instance, right? Or a class of universal optimal learners, for instance, or
yeah, I'll have to think about it. It's definitely possible that there are similar questions, or that this.
I mean, this is a very general, it's a very general framework, right? So maybe you can just apply it in different domains.
Yes, I should say we have lots of other thoughts in the original paper, and in most cases the answer is polynomial, not exponential. So
when you relax exact to approximate, for instance, right? Or
right, then we get polynomial. And also, if you want to compare stuff not to Huffman algorithm but to the entropy, then also the answer is it's actually linear, or even sublinear, depending on what you want to do. Yeah, there are lots of open questions. Like you came up with some that we didn't think of, but in the original paper we have like scores of open questions. So that's a lot of room to explore, and finding applications. Yeah, that would be great.